Okay, so here's where we're going to start. We're going to start with your questions about VARD. So, I'll make that bigger. Okay. Your goal is to ask questions that would prove that you actually watched the video. That's your goal. So, what do you got for me? On the left. Let's go left or right. Yeah.
When you substituted for, like, when it wasn't cubic and that wasn't the definition, but you substituted 5.
Yeah, ready? Mr. Seamon makes mistakes. Okay. I made a mistake.
Okay.
Yeah, it happens. Yeah.
What does a removable discontinuity do to the graph, and how do you find
What does an RG do to the graph, and how do you, Okay, next. Gare.
does the chart thing work for all?
Does synthetic division work for all polynomials?
And like when you put the finding right after the part 3, why did you only follow like -3, not -5?
I'm sorry, say that again?
Like for the asymptotes.
Uh-huh.
Why is it 5?
In finding vertical asymptotes, why what?
Why did you only have to make -5?
Was this my mistake you're talking about, Hammer?
No.
No. In finding vertical asymptotes, why are some positive and some negative?
I don't understand.
No, not yet. Hold on. We're not answering the questions yet. Other questions. It'd be really helpful if you could write these down so you can actually read them out loud and not stumble over yourself trying to come up with the homework that you were supposed to do last night. Yeah.
Can you go over the, like, what you call it, synthetic division? Because I sort of understood it,
Yeah.
but, like, I didn't...
That's the whole... Yeah, it's fine. You were not supposed to understand all of this.
Thank God.
There's no way. This is the first actual real topic that's brand new to you. This is the introduction. If you understand every topic that is thrown at you immediately, the class is either... I'm either a very, very, very bad teacher, or you're in the absolutely wrong class. Yeah.
Also, can you go over finding the asymptotes?
Balance.
Do you have to use the synthetic division to figure out the RD?
No.
So what does that do? I don't.
What
I've never
does-
seen that before.
I just said that out loud that you hadn't said it, seen it before. That's your question. Other questions? Yes, Danilo.
If you determine this and determine then VARD.
I'm sorry, what?
If you determine DIS,
Yep.
then you determine VARD.
Yep.
Are those what comes out as 5 or 6? Right?
DIS, VAR, it's 5 things. Domain,
Right, 5
intercept,
things.
symmetry, vertical
5
asymptotes.
things.
Yep.
Are those pretty much the only things you need to graph?
No, there's 2 or 3 major more things. Is this VARD all you need to know? Other questions. Let's just do questions. Yeah, one more.
Well, you haven't asymptote every time you have a rational function.
Do all rational functions have asymptotes? Right? That's what you got? Okay, so here we go. Let's answer some of these. Mr. Seamon makes mistakes. Yep. Does an RD... What does an RD do to the graph, and how do you find one? What is a removable discontinuity? What is it? Gare.
The point on the graph is there's not a possible.
Yeah, it's an open dot.
Wait, that's an RD?
It's an open dot on the graph. A removable discontinuity is an open dot. It's an open dot. The function is traveling along, doing everything normal, and everything is fine except there's one point where it doesn't
Can I ask
exist.
that question then?
Sure.
Why does that happen?
That's the bigger question.
Because of the main.
Why does it happen? They happen because they occur because the domain prevents that input from being inputted. We'll talk more about it. Yep.
What, can I ask you that?
Yes.
So, if you're in a real world situation, is there like, you literally cannot have -5?
So your question is real world implications of RDs. I'll get back to you on that. Does synthetic division, this is a big question. This is probably the biggest one right now. Biggest one. Don't get fixated on what's not important at the moment, kids. So let's keep moving. Does synthetic division work on all polynomials? Yes. This is the core to what we are now working on. More on that later. In finding vertical asymptote, why are some positive and some negative? Because they are. Some happen to the right of the y-axis. Some happen to the left. How many can you have? As many as you want, any number. What the heck is synthetic division? What does synthetic division do? It helps you factor, but that's not why. What does it do? What does it primarily tell you? What? It what? What do you mean right? What, an input value is right when it's... so what does the synthetic division do? It helps you test potential zeros, but again, what does it do? What? Sometimes it gives you a 0. It doesn't find the values of x, it finds the value of...
Function at a certain number.
You're putting in x values. So it's not finding x values. What's it doing? It's evaluating polynomials. All synthetic division does, really, is evaluate polynomials. That's it. Polynomials. We're going to do a specific one. So, how do you find vertical asymptotes? What do you have to do? What do you first have to do? You have to fully simplify the rational function. Look at the domain of the new function. That's how you find them. But the core to finding removable discontinuities and vertical asymptotes is, what do you have to do first? Simplify. And along the way, you will find the removable discontinuities and vertical asymptotes. Are there other types of asymptotes? Yes. What does it do? The primary thing it does, it evaluates polynomials, but it helps you factor. This is your factoring key. This is your best hope for survival.
But
Is this
only
VARD all you need? Nope.
Okay.
You need more. Yes.
So, but if it helps you factor...
Okay, I'll rephrase this to try to kill this next question. It's the only way you will have to factor functions in any meaningful way that have power higher than 2. If you're presented with a function of power greater than 2, it's either going to be a very specific circumstance where you're going to look at it and be like, oh, I know what that is, or you're going to use synthetic division. 99% of the time, you're going to attack all polynomials with power greater than 3 if you're factoring them with synthetic division.
So why didn't we learn this when we factored other stuff?
Because you don't need it, because there's simpler, easier ways. The factoring that you've done beforehand is twiddly, like Crayola, playing with Play-Doh, unicorns, and like
so it's only,
sugar plums.
It's not that its only application is rational functions. You can use it
anywhere you want to factor a polynomial.
That
Yes.
was my real question.
Can you use synthetic division on quadratics? Yeah, it's totally overkill. Complete overkill. Complete overkill. Do all rational functions have asymptotes? What do you think? Nope. They don't have to.
What is an asymptote? I'm so confused.
If you watch the video, I drew it
Yes,
out.
I did.
I did draw it out. Then you missed it. Did it skip around?
Oh, it was like...
Yeah, yeah, the dotted line. So you did know what it was.
For that would be that to have an asymptote, it has to have, in its fully simplified form, a variable in the denominator.
That it can't, you can't plug
So
it,
that you
an
can
input
make-
value you can't plug it in. Yes, that's correct.
So the factoring isn't...
Shh. Brooke.
So back to the removable discontinuity.
Yep.
How do you find it?
Okay, we're going to do a specific example, okay? We'll do the same example that was in the video. Yes.
Well, between an asymptote and a, like, open not closed.
Removable discontinuity, yes.
But I don't see what the difference is.
Okay, well, I'm confused because you're either, I guess people, I need to make these shorter so you guys actually see the important parts of the videos. I thought I'd explain that, but I guess I didn't do a very good job. So, here we go. Let's talk about R4. Let's talk about R4, and hopefully this will answer the lingering questions we have about vertical asymptotes and removable discontinuities. Yes. And the other lesson is I need to make the video shorter so I can make sure I stay within the 6 to 8 minute attention span of the average teenager. And it's also hard stuff. And I totally admit I put too much stuff in last night's video. What? Oh, sorry, the 3 minute attention span of the teenager. I can't do that. It took me like 6 years to read Moby Dick. Okay. If we want to look at the domain, the intercepts, and symmetry, what would be a helpful thing for us to do first?
figure out what the denominator is of 0? Or the x?
Factor.
Can't do it.
Factor. Thank you. I said something in the video. I love factoring and...
So will you.
So will you. That's right. So, can someone tell me... First of all, we hope it's nicely factorable. Everything is factorable. We hope this one is nicely factorable. Are we guaranteed this to be? No. No. Can someone tell me? Actually, it is, though. Can someone tell me what the numerator factors
I
into?
couldn't figure that one out.
I'm scared.
2 and 3.
2x plus 3 times 3x plus 3x minus 1. There's the numerator. Is that it? No, it's 2x minus 3 and 3x plus 1. Oh yeah, there it is. Quadratic factored. Bingo. What's the bottom one factor into? X minus 2 times 2x minus 3. This right here, I know it's not straightforward. You must dominate these. This is the kind of factoring you do by guess and check. You just flat out do guess and check. Don't erase anything. Keep track of what you're testing. I see this happen all the time. Kids start pairing stuff up and trying different pairings for factorizations, and they keep on erasing it, so they don't test them all. There's like 7 they need to test, and they test the same 5 over and over again. They're like, oh, this isn't factorable nicely. No, keep track. Okay, so we factored it. Let's answer these questions. Can someone tell me, raise their hand, not speak out loud, raise your hand. What's the domain of this function? Nell. Or what?
No.
Yeah, you got it. What about intercepts? What's the easy intercept?
Y.
When x is 0, what's y? Someone raise their hand and up. Go. Yes. Plug in 0, you get negative 3 over 6, and that's negative a half. What's the other intercept? Oh, we have the y-intercept. Maybe there's some x-intercepts. What are the 2 x-intercepts? Can someone raise their hand and tell me what they are? Hammer. And what? Ah, this is where we pause and say, ooh, what do you notice? Someone raise their hand and tell me what do you notice at this point. There's a contradiction in this information right here. There's a contradiction. Shh, shh, shh. Andy. Yeah, this is not part of the domain. This is not actually an intercept. Something else happens there. Hint. Hint. Okay. So, how many intercepts do we have? 2. We have a y-intercept and a x-intercept. I think we had the exact same interaction in my last class. That was pretty cool. No, it's fine. I was unclear. I asked the same bad question twice. It's okay. Yes.
Why does the 3 over 2?
Because you cannot plug in 3 over 2 into the original equation. If you plug 3 over 2 in, what do you get? Divide by 0. Can't do it. Something else happens there. We'll get to it. Symmetry. Yeah.
I have a question. I got the other x intercept is negative what?
1/3. It's not negative 1/2. It's negative 1/3. You're absolutely right. Can someone tell me about the symmetry? What is it? Neither. Neither. You plug in negative x, doesn't flip it around, doesn't stay the same. So here we finished this. Great. Now we're going to move on to where it gets to actual math land here. VARD. So the first one is vertical asymptotes. What do you need to do first? Simplify. And we've done most of the work already. We've actually done the heavy lifting because we've already... And I love factoring.
And so will you.
So if I say I love factoring, you say?
So will we.
So do we. Ready? Ready? Yeah, ready? I love factoring.
So do we.
Awesome. I'm going to shout that out during chapel.
Oh my gosh, please do.
Vertical asymptotes. Yeah, so what canceled here? So we had, here's our original. This is our original function right here. It's being cranky. I don't know why you're doing that. Anyway, we have 2x minus 3 times 3x plus 1 over x minus 2 times 2x minus 3. What cancels? Yeah, those cancels, and you're left with, we're going to call this R4 simplified in terms of x. What is it? 3x plus 1 over x minus 2. We've now fully simplified this polynomial. At this point, what's the domain of the simplified polynomial? 2. There is a vertical asymptote. What is the vertical asymptote? Exactly. The vertical asymptote is x equals 2. It is a vertical line at x equals 2. Can the function cross that line? Absolutely not. The function is either going to do one. It's going to do one of four things. It's either going to go up and down like this, or what is it going to do? The other way, or what? Or up, up, or down, down. You can either have this or that. One of four. We learn later how to figure that out, but right now we know that there is a vertical line at x equals 2 that this function cannot cross. Are there any other vertical asymptotes?
No.
No. There are no more vertical asymptotes. There's only one. You simplify, you look at the domain of the simplified function. Again, what's the only truly hard step here? Factoring. We're going to try to reduce it all to what's the hardest part, what's the core thing? Factoring. And then we're going to find the core thing of factoring. The core of factoring is the core of the core, is the really super important part. So let's go back here. We just did the first half. We just did VA. Now we need the...
What if it's not nicely factored?
Ah, then it's more fun. Let's focus on the nice ones. Removable discontinuities. What do you look at when you're trying to find the removable discontinuity?
Where x cannot be.
The other.
So along the way, what did we do? We canceled. Removable discontinuities, you look for what you canceled out. So in this case, we plugged a hole. We plugged an open dot. What open dot did we plug? Not negative 3 over 2. We plugged 3 over 2. This right here, what is 2x minus 3 over 2x minus 3? 1. By multiplying by the same thing on the top and the bottom, have we changed the shape of the graph? No. What we've done is we've created a hole. So by, and I'll get to that in a second, by crossing them out, what have we done? Eliminated that hole. That hole occurs when x equals at x equals 3/2. We know now, so this function, we know there's a vertical asymptote. It might look like that, right? It can't cross a vertical asymptote. But a removable discontinuity, here's x equals 3/2. The function is traveling along, and what happens at that value? There's a big hole right there. Actually, it's not very big. It's actually as small as it possibly can be. It's the size of 1 point. Our big question is, where does that hole occur? We'd really like to know where that occurs. Hold on, let me finish this sentence, and then we'll get to your question, okay? We want to know where that hole occurs. The problem is, if you have a function, and you have an x value, how do you go about finding the y value? You plug in that x value into the equation. The challenge here is this x value, can you plug it into this equation? No, because it's not part of the domain. But where can you plug it in?
One way simplified.
The simplified form. We have simplified it. Can you plug in 3 over 2 into the simplified form? Yeah. The only difference in shape, Hammer, could you get the lights? The only difference in shape is that this function, the simplified one, the hole is filled in. We know that the x value of the hole is 3 over 2. So if we want to find the y value, so we can... so we use that function. So what was that function? It was... Where is it? It is... There it is. 3x plus 1 over x minus 2. R for simplified was... 3x plus what? Over... So if we want to know where the removable discontinuity occurs, we plug in r for simplified of 3 over 2 is going to be 3 times plus 1 all over x minus 2. That's 3 over 2. I got to actually put in the value. That's correct. 3 over 2. And we're adding to it 1 over negative a half. So that's going to be 11 over 2 over negative 1/2, which is negative what?
It's going to be negative
11,
over 2.
which is negative 11. Yep. So do we actually know where this point is now? It is at 3 over 2, comma, negative 11.
Is this all going into a video?
It's all being recorded right now. Hi! Yeah.
What if the denominator is a 3 squared?
Then you can factor it even more, and it's still one asymptote. So you're asking that. That's a great question. That neither class came up with that. What happens if you had some polynomial, you fully simplified it, and let's say the denominator was this. Vertical asymptote at x equals 2. still a vertical asymptote at x equals 2. In that case, I'll just tell you this. In that case, we're going to get to this later. Remember how I told you the asymptotes either go up, down, or both up, both down? If the power is even, both of them go up or both of them go down. You start learning. That's later. But the point is, how many vertical asymptotes do you have right here? That's the only thing I want you to know at this point. That's it. We are compartmentalizing this. If you want drama, go see someone in another building, okay? That's all I want. We have to break this down. I'm breaking this down into small pieces as I can. DIS, VARD, and there's one more section, okay? And then once we put it all together, what are we going to be able to do?
Graph.
Actually make a picture. Yes, Furia.
I actually still don't understand why you found 1.5 to find the RD.
I can explain that later. I can't go back right now. You can watch the video or stay after school, okay? Yes?
Will a graph... Oh, we can't use our calculator because it wouldn't show us that.
If you did try zooming in, it's a really hard thing to see on your calculator because the resolution on your calculator is really, really, really low, right? I don't have one up here, but if you zoom in far enough, eventually you'll see it. But it's not the calculator doesn't go dot, 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 and make an open dot for you. It doesn't do that for you, unfortunately. So let's see if this clears things up for you. Have you ever graphed this function before?
Yeah.
It's not a trick question. Okay. So what does this look like? 45 degrees. Exactly, right. Okay, let's say I did this. Y equals, let's say, x times x plus 2 over x plus 2. What did I just multiply by?
1.
Did I change the shape of the graph?
No.
No. If I wrote this out, it would be x squared plus 2x all over x plus 2. Doesn't look like y equals x. It would be a whole at
-2.
-2, -2. Because what can't you plug in now? You can't plug in -2.
Oh, because then the denominator would
Be
be
0.
Okay.
Exactly. You can't plug in -2. So the only thing we've changed is we've added a puncture, a removable discontinuity. That's all we've done, right? That's all we've done. Let's say I gave you a graph like this. Let's say that was y equals x, and I'm telling you, let's say there was there. Let's say it was that, and let's say that was 1, that was 3, and this was -2. Can someone raise their hand and just tell me what is the equation of this graph? X times. Okay, this whole, we've already talked about that whole, so what do you have to multiply by? Can you say it so humans can hear you? Nope. Over. Times.
Oh, x plus 3.
Minus 1.
X minus 1. Thank you.
X minus 3.
Y. Oh, okay.
You have to subtract it to get, when you plug that 1 in, it needs to be a whole. So here's the thing. We just multiply by 1, by 1, and by 1. Did we change the overall shape of the graph?
No.
No.
But you changed the function.
We did. The function is
Not
different.
changed on the same function.
It's not the same function, but overall, did the shape change?
No.
Did we warp it? Did we do some crazy thing with it? No. If I multiplied this out, could you multiply this out, the top?
Yeah.
Sure. Would it be kind of annoying to multiply out?
Yeah.
Easy to make mistakes? Yeah. Could you multiply the bottom out? If you did, the top would be a quartic. It'd be a 4th degree over a cubic.
Y.
Now here's the thing. No questions yet. A quartic over a cubic because there's 1, 2, 3, 4 x's. 4th
Okay.
degree. Now here's the thing. Let's say I multiplied it out and just gave it to you. Would you be able to immediately identify it as a line with holes in it? No. What would you need to do? What's the key thing you'd have to be able to factor? So you know how to multiply. That's pretty easy. Going in reverse, factoring, that's pretty. You need some guideposts. You need a plan of action. The key thing that's going to help you, 2 things: synthetic division and potential rational zeros. Before we jump into that, we're going to take a little brain break, and I'm going to give you an actual fun present. Synthetic division. All synthetic division does is evaluate polynomials. That's it. All synthetic division does is evaluate polynomials. So, if you want to evaluate a polynomial, you use synthetic division. If we look at R5, this is something you're going to have to do tonight. We've already talked about how The key to everything, the key to this step, all these 5 steps so far, is being able to what? The key is being able to factor, being able to simplify, and the key to simplifying is being able to factor. Top or bottom is easier to factor. What do you think? Bottom. Why? Smaller numbers, absolutely. So, you need to find numbers that make that polynomial equal 0. Why? You do that because if you looked at a polynomial like this, that's the same thing as x plus 2 times x plus 3. If you graph that polynomial, what does the graph look like? Well, at -3 and at -2, it crosses the x-axis, and you end up with a parabola, correct? These are called what? -3 and -2. Those are called roots, which are also called zeros, also called intercepts. Yes, those are all the same. Those are roots of the polynomial. When you say roots, I mean a 0, I mean an intercept. What are these called? X plus 2 and x plus 3. Those are called what of that? Factors. Now look, -3 correlates to x plus 3, because when you plug in x plus 3, you get. -2 correlates to x plus 2, because when you plug in -2, you get 0. Exactly. So, if you find zeros, roots, or intercepts, what do you automatically find? Factors. If you can find a 0, what have you found? A factor. If you found, let's say you know that 5 is a 0, what's the factor? X minus 5. Let's say pi was the 0. What's the factor? X minus pi. If r is the 0, what's the factor? X minus r. So if we find zeros, we can factor. We're good with this? So we need to find, in this one, x, what is it, x cubed minus 4x squared plus x plus 6. Please sit if the bell rings. It's only a couple more minutes. We want to solve that, right? We could just start choosing numbers. How many numbers are there? Many. We need to shave that down considerably in order to do this within our lifetime. We use something called the potential, this was in the video, rational. We find potential rational zeros. These are, simply put, potential rational zeros. If this cubic has rational zeros, they will be in this list. Are you guaranteed to have rational zeros? No. You could have 0, 1, 2, or 3 of them. If there are any rational zeros, they will be in this list. This list, what 2 numbers do you need to look at? Anybody remember from the video? First and last. You look at 6, and what are the factors of 6? Yes. What are the factors of 1? 1.
So
1 is your favorite number here, because you turn this into the list by doing all the possible pairs. Numerator and denominator. So 1 over 1, 2 over 1, 3 over 1, 6 over 1. What would happen if this was like 4 instead? You get more. But now, how many do we have? Actually, 8 of them, because there's plus or minus, right? There's 8 of them. Now, that seems like a lot, but how many did we start with? I need to finish this. They start with all of them, right? So, what you do now is you need to test them. You could just plug them into your calculator and see which ones come out to be 0. What you can do now is use synthetic division. What are the coefficients of this polynomial? 1, -4, 1, and 6. If you misplace one negative sign on this, it blows up. Let's pick a number we want to test. In the video I told you what numbers you should start with? Small and positive. So let's test 1. The first thing you do is you drop down 1, and now you just start multiplying by the number that you started test. So you multiply by 1 and you get, add, multiply by 1, add, multiply by, what this tells us is that f of 1 is, so therefore x minus 1 is not a factor. You do not erase at this point.
X minus 1 is not.
Is not a factor. You don't erase this. You need to keep track of the ones you've tested. What should we test next? Let's try 2. Same coefficients. 1, -4, 1, and 6. 1, 2, -2, -4, -3, -6, and 0. Is that right there? You're going to be totally programmed. When you see zeros, you're going to be happy. Because you now know that f of 2 is 0, so x minus 2 is a factor. So you now know that x minus 2 times something is equal to our original polynomial. We need to know what that something is, and the key is, this is where synthetic division is so powerful. It tells you it, but also, this right here, it's sitting there right in front of you. Do you remember where it is?
Isn't it those numbers that are...
It's the numbers in front. It's the numbers in front. So you see what's left over here? This is the constant, this is the x, and this is the 1x squared minus 3. You are now in your home free. You're in happy land because you're in quadratic land. Do you like quadratic land?
Yes.
Yeah. Someone said no. You need some dissonance in there for the harmony, right? X minus 2 times x minus 3, x plus 1 is equal to the original polynomial. Is this fully factored? So if you fully factor the top and fully factor the bottom, you can find the domain, the intercepts, symmetry. Well, symmetry is unrelated, right? Vertical asymptotes and removable discontinuities. The key to it all is simplifying. The key to simplifying is factoring. The key to factoring is synthetic division. Your homework tonight, everybody. Your homework tonight. I would like you to do 3 things. 1, look up the cubic equation. You know, the cubic, what I mean by that is the cubic formula. You know, there's the quadratic formula. Look up the cubic.
Isn't ax squared plus bx plus c?
Ax cubed plus bx squared plus cx plus d. You use a, b, c, and d, and there's a formula. Quadratic formula is negative b plus or minus the square root of b squared minus.
Okay.
Find the cubic version.
Because like if you look up quadratic
Second, disVARD on R5 and R6
So they're both R5.
are what?
They're both R5.
Oh, you remember Mr. Seamon makes mistakes. I know it's hard to believe I'm not perfect. I know you weep inside a little bit when you realize that. And number 3, everybody, watch rational functions part 3. I'm gonna make it short. I'm sorry. You got the homework, everybody?
Sorry.
5 and 6.
Oh, sweet. Are we just whack?
Oh.
Across the party. I need you to write this. Mr. Seamon, is it...
Hold on.